Thank you very much for that kind introduction. Can you see my screen?
Yes.
Okay. So what I want to tell you about is actually, so this is a very grand title. It's actually a little more down to earth. Basically two things. One is regioselectivity and one is reaction discovery. And what they have in common is some component of quantum chemistry.
Yeah.
Which
I'm sorry to interrupt. You are showing the presenter's
view. Thank you. There we go.
Welcome.
Thanks. So given my background, the sort of what ties these things together is the quantum chemistry. And so what role does that play now that we have all this machine learning? So first thing, regioselectivity. So probably the reason I was invited to this, I'm not a synthetic chemist, but sort of one contribution I've helped make is a method by which you can predict where bromination happens. And so that's, I'm told, valuable to synthetic chemists because as molecules become more complex, it can be harder to predict. And so this allows you to sort of use these bromination steps in the later stages of synthesis because you're now able to predict where it will react given many possibilities. And it's actually, so I should say this is the work by Jimmy Coleman, and it was done in collaboration with people at Lundbeck, which is a pharmaceutical company here in Denmark. And the idea is basically that it's based on an old empirical observation, I think back from the 60s, that the proton affinity is correlated with the reaction rate. And so what that means for regioselectivity basically is that you have to find the site, or if you find the site with the highest proton affinity, then you also find the most likely site of bromination. And so we basically wrote a program that calculates this automatically, and it's based on semi-empirical methods, which are somewhere between machine force fields and DFT. So it's about 1,000 times faster than DFT and maybe 1,000 times slower than force fields, but it's still a quantum mechanical method, so you can make and break bonds. And so we chose one particular level, basically, so a level of a semi-empirical method and also a choice of solvent. And we did this. We found these parameters based on a data set of about 100 molecules. Or reactions, and then we applied it to about 400 more, and based on this, we had a success rate of about 90% or so. So this is back in 2018, and so what was new, at least for me at that point, and was also fairly new back then, was sort of the level of automation. So one thing that sort of kept quantum mechanics from being actively used by synthetic chemists is the lack of automation. And the other is speed. So semi-empirical methods are very fast. So the last bottleneck was really automation. And we set up a workflow that basically allowed you to, sort of in quotations, to draw the molecule in ChemDraw, copy the SMILE string, and paste it in, and then it would give you the kind of prediction you see here, where green is the most likely site of bromination and red is the second most likely. And so because of this automation, we could also make it available as a web server. So if you go in here to regiosqm.org, you can now simply insert the SMILEs directly from ChemDraw or some other drawing program, and then it'll give you a prediction. And so it's completely automated, and so there are actually some papers out now where that's being used by synthetic organic chemists to help in the synthesis. Actually, I've sort of I was reminded of this when we talked about education just now in the era of automation, and so that's also, we're actually also using it in education here, and I'm now told that occasionally the answer to the question, where do you predict the bromination to happen and why, the answer will be here because Regiochemical told me so. So this is it's sort of a calculator of sorts. So this is freely available. But one sort of, in general, one bottleneck for the use of this was the fact that it relied on PM3, which is free to academics, but costs money in industry. And so when I started a collaboration with Andreas Göller at Bayer, the first step really in advancing this is to switch to something completely open source. So we now use another flavor of semi-empirical theory that's actually that's completely open source and available to everyone, and it doesn't affect the accuracy at all. So that was more of a technical switch, but we also added some other capabilities. So one is tautomer generation. So the regioselectivity is affected by the tautomer you input. And so it's, if you input the wrong tautomer, you'll get the wrong prediction. And so we now automatically generate several tautomers. We have an energy cutoff. It's actually tautomer selection is actually a more difficult problem than regioselectivity. So it can be very hard to actually predict the right tautomer. So essentially what the program does is present several options that are automatically generated and then leaves it for the user to choose the correct one. We do give our best guess at the tautomer. We do indicate it here. So this is basically the relative energies between the two. But it's probably better that an expert sort of decides. So that was one improvement. The other is reactivity prediction. So basically, in addition to saying that it reacts here, we also have some measure of how likely it is to react or under what conditions. So this is based on the fact that we also compute the proton affinity. So in the old version, we would just compute the proton affinity and look at the highest value. But now we can actually, we did an analysis of the proton affinity in our 500 molecule data set. And so we basically found that we have an almost Gaussian distribution where most of the molecules lie, but we also have some with very low proton affinities, and we would predict these to have low reactivity. I'm also told by organic chemists that these functional groups actually make sense, that you would think that this has low reactivity. And we also have some with unusually high reactivity. So we can, in addition to saying where it would react, we can also say a little bit about how, let's say, how likely it is to react, or how mild or harsh the conditions would be. So we published that. That came out last year. That, again, now it's completely open source, and we just need to update the web server to sort of reflect these new changes. So that has been published. Now I want to say a little bit about what we're doing right now. So in our paper, or as we were making the second version of Regiochemical, there are several machine learning papers that came out, notably one here by Connor Coley and his group. And so in that paper, we then compared for this relatively small set our performance. And so that's, that becomes kind of tricky. But I would say in general, they're roughly of the same accuracy. Probably the machine learning is a little bit better. Here's for all the molecules, and here are for the molecules that only have one reactive center. And as you can see, the accuracy here is somewhat better than the accuracy here. This is something I'll come back to. The main point I want to make here is that if you just use it in a retrosynthesis setting, using programs here, IBM RNX, that are not specifically designed to predict retroselectivity, right? Then there is a significant improvement. So there is, these things are relatively sort of hard to predict with a very, very general method. And so it is good to have more specific methods focused on regioselectivity to augment these more general tools. And of course, that's sort of the long-term goal with this, right? Is to with a accurate prediction of regioselectivity, to open up some new synthetic routes that these programs can predict. Okay, but well, what I didn't say, but what is sort of implicit, right, is that not only is this machine learning model here from the Kohler group as accurate, or maybe even more accurate, right? It's much faster. So this can make a prediction in a few milliseconds, and we need minutes to do it for the same molecule. So where does this kind of method fit in the scheme of things now that we have machine learning? And so that's what we're sort of working on right now. So we're working on our own sort of machine learning model of this. Now, instead of 500 bromination reactions in the previous set, we're now working with 27,000. So and about 100,000 reactive centers. So we're working with a much bigger data set, the one similar size to the one the Kohler group used in their method. So we use, this is just some machine learning stuff. What in this particular case, our descriptors, the way we sort of describe the atoms to the machine learning model, is based on semi-empirical atomic charges. And so then there's sort of a convolution step that basically tells the machine learning what charges sit next to what other charges. And that's sort of how we featureize the method. And so to test this, we've developed 3 sets. So we have what we call a train and a test set and an unseen set. So basically, we've gone into this set of reactions, and in some of these, there are reactions that are very well represented. There are a lot of examples. And then there are some unrepresented. And so we try to cluster the more well-represented reactions in the train and test set. So basically, we find molecules that are within a certain similarity distance, a tanimotor distance. And if we find enough of them, we throw it into these 2 sets. And then the rest, all that's left, the special cases, the less represented molecules, we throw into this other data set that we call unseen. And then we split this seen data into a train and a test set and use this to train. So, okay, so a lot of numbers here. Let's sort of take it from the top. So the first thing is that what I'm showing here is not accuracy anymore, but it's what's called a Matthew correlation coefficient. So it's basically a correlation coefficient. And the reason I use it is because it also takes into account false positives and false negatives. So false positives, this is where we say the bromination will happen at this site, and it doesn't. False negatives, we say that there will be no bromination at this site, and in fact there is. And so the accuracy, just looking at the accuracy, sort of misses that out. So I'll come back to this point, accuracy versus correlation coefficient. But basically what you have to know here is that the closer this is to 1, the better. And so the first thing is to take a very, very simple model. So this is called one nearest neighbor. So basically it just finds the closest molecule that it's seen in the training set to make the prediction. So this is basically memorization. It just, you give it a new task, and it It goes back and looks up the molecule that is closest to this as far as the descriptors are concerned, and then gives you that prediction. And so as you can see, you get actually a reasonable correlation coefficient for the test set, but for the unseen set, so molecules that are somewhat different from what is in the training set, right, it really fails. So a correlation coefficient of 0.5 is not very good. So this is sort of this is what we have to beat. And so here's our sort of our best version. This is the light GBM, sort of extensively tested and optimized hyperparameters. And we get a correlation coefficient of about 0.81 on the test set. And so that's actually, that's fairly good. That, as you'll see, that corresponds to an accuracy in the 90s. And if you now compare it to our Regiochemical, and so here we've actually gone ahead and, in addition to the semi-empirical methods, we've performed some actual ab initio DFT single points. So it's even a better version than the Regiochemical 20 model. It's the sort of the souped up version. And as you can see, we're not as good here, right? So machine learning on a large data set is going to beat quantum chemistry predictions for molecules that are very similar to what's in the training set. But if you go over now and look at the unseen set here, actually the performance is about the same, right? And notably, the performance here in the test set and the unseen set is basically the same, right? Because what the quantum chemistry brings to the table, right, is that it's much less dependent on what's in your training set or whether it's seen the molecule before. So the test set performance here is a very good predictor of molecules that it hasn't really seen, whereas that's not the case for light GBM or for machine learning in general. So, but still, even so, right, the performance is actually about the same for the unseen set, which is quite impressive, right? And this, of course, is 1,000 times faster than this. So what is the role of quantum chemical predictions in all this? Well, it is that we developed the quantum chemical method, right, basically using 100 or so, or in the second case, 500 or so molecules, which is probably sort of overkill. So if you have much larger data sets, like, you know, in the 20 or 30,000 different molecules, then it's going to be very hard to beat machine learning. But what if you have only 500 or so, which is actually a very common thing in you know, that's a respectable size of data for many chemical applications. What if you only have that? Well, if you train your machine learning model on this small data set, right, you get a very, very poor performance, both for the test set and the unseen data set. So what can you do then if you don't have any more experimental data? Well, you could generate more data, synthetic data, using quantum chemistry. And so this is what we've done here. So here we've generated the data for the training set. So about, what was it? Well, thousands of data points. And then we fitted the model, the light GBM model to this. And as you can see, we're basically able to reproduce the performance of the quantum mechanical calculations, right? We're a little worse when it comes to the unseen data, because this is still a machine learning model that depends on the training set, right? But we're much, much better than using additional data to augment a small training set. It gives you much better results than just training on a small data set. So actually, that's one sort of takeaway message of this talk, is that the quantum data can be used. If you have a reliable quantum model, you can use that, even if it's semi-empirical or partially semi-empirical, you can use that to augment small training sets. And so this sort of gets me back to accuracy. So and this is why I focused on this Matthew correlation coefficient, which has false positives and false negatives in it, right? If you just look at the accuracy, first of all, for this very, very simple memorization model, right? You see the accuracy is already very good. What you have to keep in mind is that these, in general, these are very often unbalanced data sets, meaning they're very, most of the atoms in the molecules you have are non-reactive. And so you can actually make a very good model, machine learning model, in terms of accuracy by just saying none of the molecules are reactive. And if you do that, right, you get an accuracy of 76%, which means that 76% of your atoms in the data set are just not reactive. And so if you say all the molecules are reactive, are unreactive, then you get a good accuracy, but you still get a very bad correlation coefficient. In fact, it's 0 because you have no true positives. Right? So 76, right, is what you have to beat. And so even if you just look at the accuracy, right, even a small data set model like this, if you just look at the accuracy, you'd be tempted to say that that's really not too bad, and that, you know, adding thousands of more data points only gives you a relatively small improvement in the accuracy, right? But what this doesn't account for is the great reduction in the number of false positives and false negatives, right? That's reflected in the correlation coefficient. So this is just a little bit of an aside, but I know there's a lot of machine learning people who may be interested in this. Okay, so future plans for this is what I've sort of tried to show in this very busy slide. So the bottom line is just that here we had a reaction, we found a correlation to something we can compute by putting a proton on, right? So here we add a proton to this, we look for the best place to add the proton, and that says something about the regioselectivity. Okay, so if you can take a proton, you can put a proton on, you can also take one off. And so that correlates with a lot of with regioselectivity of a lot of reactions that goes through an acidic, or that happens at an acidic proton. So you could imagine regioselectivity for these molecules to be predicted by computing basically the pKa of the CH bond. Same with radical stability. Same with carbocation stability for other types of reactions. And finally, there are some where it's where you have a directing group. So basically, it depends on an attractive interaction between your catalyst and some nearby group, not the intrinsic reactivity of the site itself. But you could actually model that in exactly the same way. So you could put a model catalyst on all different sites, right, and conclude that this is the intermediate with the catalyst that's most stable, and that, at least in this particular case, correlates with this directing group induced regioselectivity. So that's something we're going to start up very soon to sort of expand the powers of regio SQM, and we're going to do that both with machine learning, possibly augmented with some synthetic data from quantum calculations. Okay, I don't have a lot of time left, so I just want to quickly go through the next thing here. So basically, one way to sort of, in broad strokes, to define regioselectivity, right, is that we have a set of possible products and we have to choose the right one. Okay, but in principle, quantum chemistry can do more. It can do much more. It can, in principle, tell you what the reaction should be. We've done that for many years. The main problem is just that it hasn't been automated, and in many cases, it's too slow, right? If you have robots now that can search the reactive space for new reactions, you have to be faster than the robots. So that is possible. That is becoming sort of I would say in another 2 years or so, that'll be sort of a normal day for theoretical chemists in atmospheric and combustion chemistry, where the molecules are small enough. And so there are to be done quickly. So there are programs now that you can download that have automated it completely. You basically put in a molecule and it spits out reaction rates for all the different reactions that can occur in the atmosphere. Main problem with this is that it's basically based on reactivity rules, and so you can't really take these programs and give it an organic molecule and expect to deal all the reaction. So in order to generalize this, we have to, if you want to do it this way, right, you have to generate all these rules for organic reactions. There is so Fernanda Duarte has started this process with in a very promising looking software package here, and as she and her collaborators add more reactions, this could become a very powerful program for reaction discovery. We're taking another approach that's a little bit more sort of general and hands-on. And so basically, so there's a lot of equations here, but basically what we want to do is use dynamics. So we simply want to simulate what happens if you put two things together. How do they react? In order to do this, you have to do it with a method that can make or break bonds. So again, that's semi-empirical methods. And you also, these reactions are rare events. So you have to sort of force it to happen. Otherwise, you'll just sit and wait forever. And so that's known as metadynamics. And one sort of flavor of this has been developed by Stefan Grimm. So basically, it forces the dynamic simulation to explore places it hasn't been. Okay, the question here is, when it does that, does it explore the reactive space that has the lowest barriers, or does it do it in some other, is it forced in some other direction? So that's sort of the key question here. If this is true, if the answer to this is yes, then in principle you can find, you can use this to find the low barrier reactions that'll tell you what products are most likely. So the idea is that you start with reactants, you run the MD, you see what products it makes, and then you have to then estimate the barrier. And so we do that with another method devised by Grimm that basically extrapolates between the two. Then we get a barrier estimate, and we pick estimates that are relatively low value, and then we actually find the proper DFTs, transition states. So the question is how you test that, because you have to test on systems where you know for sure that you found all the low barrier reactions. And so there's a few of those. We took this data set here, which is published here. Here they very carefully looked at all reactions, identified the three lowest ones. So it's basically what happens to this molecule, how does it fall apart? And with this metadynamics approach, we're able to identify that these reactions are the ones with the lowest barriers in about 15 minutes using relatively modest computational resources. So on the order of maybe 100 or 200 CPUs. So 15 minutes, this is here you're more than competitive with these reaction discovery robots. The main challenge in all of this, right, is to find the hyperparameters here that sort of pushes the molecules around and forces it to explore other parts of the reactive surface. So the results you get are very sensitive to these parameters. But basically what we show here is that, at least for this molecule here, one set of parameters allows us to find all of this. And what we're doing right now, so the previous study that's now on archive, what we're doing right now is trying to see whether this methodology we developed, does that work on any other molecules? And so, or reactions. So again, there's not a lot of data. There is this data set here from, again, from Grambo, Green and co-workers, where they looked at a much larger data set. So you have about, with the expensive DFT, you have about 12,000 barriers. The problem is, out of these 12,000, there's only 27 that are low barriers, right? Which are the barriers we're interested in. But nevertheless, we ran our metadynamics on this. We generated actually a lot of products, different products, found the barriers. 288 of those are relatively low in energy. We use a slightly higher cutoff here because this is just an estimate. And we now sent these on to as starting points for more expensive DFT calculations. And so far, this is work in progress. So far, we've found 20 of the 27. And so what we're looking into now is whether we have to tweak some of these hyperparameters to get the other reactions, or whether something else went wrong. And we also have to check, because we found many more products than 27. So are we also finding new reactions that maybe has comparably low barriers that this approach here used by Gramberg and co-workers missed? The main point is that you can do this relatively fast, right? So you can check all these. You can generate a huge amount of possible products in a matter of hours, and you can actually estimate the barriers in a matter of minutes. So that's what we're working on now. Stay tuned. And that brings me to the end of my talk. So just sort of to summarize, so in the regioselectivity, if you have very large data sets, then it's going to be hard for quantum mechanics to beat that. Your machine learning model is just going to be able to learn what it needs to learn. And it can make predictions at a fraction of the cost. But here we're talking thousands of reactions. If your training set size is much lower than that, then I think to have something usable, you can, and I think actually you must augment this with quantum mechanical calculations in order to expand chemical space coverage and get an acceptable ratio of true and false positives. And so we're going to use that approach for more types of regioselectivity for different kinds of reactions. Reaction discovery. One approach to this seems to be this metadynamic approach, where you just sort of let the thing, you put two molecules together and let them do what they want, right? But it's obviously still early days. I should mention that we're not the only ones working on this. These are two preprints that just came out, one from Alain's group and one from David Glowacki's group, with very, very similar ideas. They're also getting very sort of promising results. But I think they'll agree that it's still early days. Maybe in 2 or 3 years, we might have something where quantum chemistry can actively sort of help suggest new reactions to check out. One bottleneck here is benchmark sets, where we know for sure what the answer is, and that are not only thoroughly done, but also more realistic in the sense that they look more like organic reaction mechanisms than the ones we're currently testing our method with. Okay, that's it from me, folks. Thanks very much. I'll be happy to answer any questions.
That's great. Thank you very much, Jan, for an excellent presentation this morning or this afternoon, depending on where you are. Just while we start getting a few questions coming into the Q&A, if I could just kick off. How far away do you think we might be from actually being able to, not necessarily 100% accurately, but realistically predict synthesis outcomes just purely on a quantum chemical type basis for the types of molecules that a lot of us are typically interested in?
Yeah, I mean, 5 years, I think, until you see something, sort of the proof of concepts. Well, maybe that's 2 or 3 years. I mean, you could argue that Alain's paper, for example, actually has some proof of concept there, where he does have some completely realistic looking molecules where he does make some good predictions. Whether it's sort of a priori, or whether you still have to hold its hands, this method, that sort of remains to be seen. But maybe in 5 years, if we're lucky, we could have something where people really can sort of type in A and B, and the program comes back in an hour or so with with the products. Now, this will be sort of a series of possible products that still has to be tested. There'll be nothing in there about reaction conditions or anything like that, or even what solvent to use. That's a much harder question. But I think it's something where it'll say, well, no, the barriers here are way too high. You won't get anything with reasonable reaction conditions, or this is what should pop out. I can't tell you under which conditions, but it should be there in your mixture when you're done.
Okay, so it's a few years away, but we should start to get some indications, and it will provide us with at least some information, and in some cases, perhaps some really quite useful information.
I hope so. Yes. Yeah.
Good. Thank you. So we've got a couple of questions coming so far on the chat. The first one is anonymous. Thanks for a great talk. Would it be possible to predict stability of a molecule by finding a bond which can be broken easily? I hope to hear your opinion because it seems promising as one of the applications of your results.
Yeah. Actually, I think maybe stability is actually the first sort of application of this you'll see, right? So you don't start with A or B, you just start with A, and you just see if it falls apart. That's probably the sort of the that's a slightly easier question because there's only one molecule in there, and that's basically sort of what you saw with that. That's basically what atmospheric chemistry is. It's, you know, something comes up in the atmosphere, it's attacked by something, or it's maybe just generally unstable. And what does it fall apart to? And so that can actually be done fairly soon, I think, at least for something that's, you know, very unstable. Yeah. Good.
Got one here from Kiel Yorna, if I pronounced that correctly. Apologies if I haven't. Thanks for a nice talk. Regarding the tautomer problem, did you try any energy ranking of the tautomers, for example, with the CREST tautomer model or the RD-kit heuristic rules?
Yes, so the RD-kit heuristic rules are not, so I've talked to Greg about this. So those rules are not there to predict stability. Now, we haven't used the CREST, but we sort of have a similar approach since it's still based on the same semi-empirical method. It's just not accurate enough. In fact, if you look at even very, very high-level quantum mechanical calculations on tautomer prediction, they're actually also not very good. And the real problem lies in the way the solvent is modeled. So we sort of gave up on the exact ranking fairly soon because there are these papers in the literature where much more expensive methods actually fail. And the main reason, right, as you know, is that even a 1 kilocalorie per mole error, which is tiny for us, right, but that has a huge effect on the distribution of tautomers. That one's just tough.
Okay, thank you. Again, apologies for pronunciation. Siquan Wang asks, I'd like to know if your metadynamics method can selectively explore the chemically more interesting reaction pathways when many relatively uninteresting low barrier pathways are present. For example, exploring the CH bond activation of a long chain alkane without sampling all possible dihedral angle rotations. Thank you.
Okay, yes. I mean, two points there. I mean, the first one is that you do have to, at some point, be aware of what the lowest barriers are, because that's how the molecule will react unless you somehow constrain it. So you do have to know what sort of the low barrier channels are before you can look at what you think is more interesting, because if they're there, the molecule will just fall apart otherwise. That being said, there are ways to basically restrict the reactive space that you're looking at to a subset of atoms, if one wanted to do that. Yes.
Okay, got one from James, which has just come in. Afternoon, James. Thanks for the great work. How do you factor solvent and temperature effects into the regiochemical outcome of halogenations and predictions?
Yeah, so we pick one solvent. And basically what we found by testing against experimental data is is that one of the solvents is, we find the one that we feel is most representative of the other solvents. It actually doesn't really affect the results very much. And temperature, we don't take that into account at all. So the main, the only thing we really have is this reactivity prediction, right? So we would expect that molecules that are very, what we would call unreactive, meaning they have a low proton affinity, you probably would have to run those at higher temperatures to get the same, to get a reasonable reaction rate. But it's not explicitly in the simulations.
Okay, and finally, it's another anonymous one, unfortunately. It's paraphrased as a naive question, but I think it is actually pretty important. How have you tackled splitting up your training and test set and its effect on model metrics when you have close performance to a baseline model?
Yeah, so basically, so that's sort of what we did with this, what we call the unseen set, right? So we find groups of molecules that are well represented just by looking at the similarity to other molecules. And so if we find molecules that sort of cluster in a region, right, then we'll throw that into our training set, and the rest will go into this unseen set, which is not the test set, it's yet another set. And so it's basically just looking at the molecular similarity. But you can that only really gives you, in my opinion, reasonable or insightful answers if you have a very large data set. Right? So we're talking many thousands of, I mean, in this particular case, we have over 100,000 atoms, right, that we categorize. Doing that for small sets, right, it's sort of, yeah, it's hit and miss.
Okay, so with that, I think we probably should close the session. Thank you, Yen, for your presentation. Again, some virtual applause, I'm sure. Also, thanks to both of you for a very interesting, educational and informative couple of seminars to kick off this last day of the conference. Thanks to Rajat for organizing and inviting us, and thanks to Mark for sponsoring this particular session as well. Thanks to everybody. Sorry we've overrun a little bit. Hopefully you've all got time to rush off and grab yourself a cup of tea or a cup of coffee before we reconvene. Thank you very much.